Thank you. Thanks, first of all, for the invitation, the opportunity to say a few things here. I've chosen a bit of broader topic. I will give you a couple of examples of CSE and HPC education, what happens within classrooms, but what can also happen outside classrooms. So why do we consider computational sciences and high-performance computing together or in the same context? First of all, both have been drivers for each other over the years. HPC drives CSE, CSE drives HPC, and of course computational scientists and engineers are probably the group of professionals with the highest probability to have to deal with high-performance computing in their future career, either in academia or in industry. So an integral look makes sense, and this includes also, as I think, data. The focus in the following will be here on university stuff. Of course, the compute centers have also developed quite elaborate programs, especially for professionals then. So what are the challenges? The first challenge is the discipline question. This is a somewhat nasty and not answered question. So are these fields, are these disciplines, computational sciences? Most people say, at least from this field, yes, but there is no field, and the others don't feel responsible. So there are no clear regulations what to teach when you want to introduce a computational science or a high-performance computing program. That's different in mathematics. When you start as a university, you want to start an undergraduate or graduate mathematics program. Tons of associations come from all sides and tell you what you have to teach, when, and what you should not do. So that's one challenge. Then, of course, if we make a specific program in computational science, high-performance computing, we typically have students coming from different fields, from different bachelor fields, for example. So how to deal with that heterogeneity, that's a very important thing. Some are very experienced in programming, others have probably more strength in the mathematical background. There's also no broad consensus what the hell is needed. So if we look at the computational sciences programs even, we will find a couple of them that are not that much programming or high-performance computing related, because they focus more on mathematical models, for example, or on the applications, and not that much on the implementation part. And of course, we have not only to discuss what about the programs, we also have to discuss how we can attract people. There have been years where probably HPC was a self-runner. These days there are a lot of sexy topics around in computing, in computer sciences, and it's not self-understanding that you get the best brains, and of course that's what everyone wants for computational sciences or for high-performance computing. So I would like to direct your attention to a workshop that has been 2 years ago, Future Directions in CSE Education and Research, which was jointly organized by the CSE branch of SCIAM. So that was the American part, and as a European part, the European Exascale Software Initiative. Around 30 people from all over the world met in Breckenridge to discuss a bit, well, what is the future orientation, what is also the self-understanding of computational sciences, and how is the interplay of computational sciences, high-performance computing, and data science. So we have now, after 2 years, a close to final version which just has been distributed. I just want to point on one figure out of this report, which I think very nicely shows the close relations. You see here on the left-hand side, the red thing, that's a well-known thing, Moore's law, which is basically hardware development. And the black thing is just one example of algorithmic development. How did the speed of how you can solve a linear system of equations evolve? Starting with a classical Gaussian elimination and ending up with the most elaborate multi-grid algorithms we have. And what we see is that the progress is roughly the same. So it is very clear that you can get the best out of or for a specific problem only if you are an expert in exploiting the machine, but if you are also an expert in choosing the right algorithm. It makes absolutely no sense to take an application code and to tune it for weeks on a new hardware if the algorithms are lousy. But that's what frequently happens. On the other hand, it makes no sense as a mathematician to say I have the fastest algorithm, I don't need parallel computing. That's also, of course, nonsense. You have to do both. And on the right-hand side, you see that the increase of challenges is also exponential. So if we start on the lower left corner with a simple scalar Laplacian equation, so the simplest PDE you can probably imagine. And if we look how this evolved over the years, over the decades, multi-scale, multi-physics problems, uncertainty quantification, data-driven things. There you see that the expectations, the requirements also go high. So it's clear that also the education has to reflect this. Computational plus HPC plus data. So hopefully the report will come out in the next week, so stay tuned. Okay, now a few remarks on what we do with programs, a few remarks on what we do with specific course elements, a few remarks on out-of-classroom things we think are very important, summer schools, doctoral retreats, and competitions. So programs. Of course, there are specializations in the existing programs in computer science and engineering in mathematics, but we also have introduced a bit more than a dozen of years ago two computational master programs, computational mechanics and computational science and engineering. They are very similar from one perspective, but they are very orthogonal from another perspective, because computational mechanics looks at the thing from the needs of a specific discipline, mechanics, so fluid mechanics, structural mechanics, whereas computational science and engineering looks from a core technology, from a mathematical and from a computer science perspective on that. We have introduced an honors course, honors class for the best of our students, which is a Bavaria, so a statewide program. And we are now going to start this fall 2 data-related courses, master courses, also in this family, mathematics and data science and data engineering and analytics. So our CSE program is very well established now. We get 300 to 400 applications every year. We have typically a beginner's class of 25 to 50. And the interesting thing is that we have more than 90% international students, which is completely unusual for a German university. We have 4 pillars of education. So the 3 pillars are classical, mathematics, computer science, and the applications. But we also have a 4th one, scientific computing, because we think that it's much more than just adding modules. It's more than taking a bit here, taking a bit there, putting it together, and then you have a nice new program. You also need to design a couple of genuine modules that really distinguish that program from a pure mixture of other ones. Some specialities, maybe we encourage our students to do some things elsewhere, which is maybe astonishing. We send our students for master thesis to other universities, to national labs, to Max Planck institutes, to industry. Some say, you are stupid, why do you send out your best students? Well, the reason is hopefully they will come back and then they will be even better. Sending someone out is always a win, and I think that's a very important component of our program. We also were the first computational sciences program, at least in Europe, that had a mandatory software engineering course. Typically, the high-performance computing persons are not software engineers, are more hackers, programmers, and they also feel that most of the things you find in a software engineering textbook is not only not valuable, it's even harmful to what you do in high-performance computing. For some things that's right, but I think if you look at the size of today's simulation packages, you can no longer afford this position. So you need professional software engineering also in computational sciences and in high-performance computing. So our master's program in data engineering and analytics, I just want to point out on 3 driving ideas which were behind. The first one is informatics, computer science has to be in the core of such a program. But of course, there is much more if you want to do a data science program. The second point is there is a necessity that the students get experience in both the technology part and in the analytics part. We don't think it makes sense that you have database experts who have not a real idea what data analytics really means in terms of algorithmics. On the other side, it's also probably not that helpful to have data analytics experts that do not really know on what kind of machinery and with what kind of technology the problems are solved. That's why we coupled this engineering and the analytics part. And everything is also part of a very novel thing. It's the first thing of that kind. A big problem in education, especially in that kind of interdisciplinary education, is that all programs are residing in departments. And this automatically produces some silo climate. And to overcome this, we have now introduced the first integrated study program, which is a TUM, a university-wide program, which gathers and coordinates all data-related activities in all departments. So not all departments will make programs. Medicine, for example, said we need a couple of courses that our students get the right feeling, what are medical data, how to deal with medical data, what are the specialities of medical data compared to Twitter data or plasma physics data. But these are all data-related questions, and we have now one overarching structure for the whole university that treats these kind of questions together. Okay, that's for the programs. For the courses, I want to give you two examples. The first one is something we have introduced 2 years ago, an interdisciplinary lab turbulent flow simulation on high-performance computing systems. So the title does not sound very spectacular. The starting point was a competition. So there's an award at my university for very innovative ideas in teaching. And the innovative thing here was we wanted to make it teamwork focused from the very beginning, and we want to make it cross-disciplinary. So here in this case, mechanical engineering and informatics students. So we wanted to keep two cohorts, to bring two cohorts with a completely different background together, deliberately. So mechanical engineers who are very experienced in flows, but who are typically, at least the ones we had, not that well in programming. And on the other hand, we have computer science students who have been real experts in the programming part, but have no idea what conservation of energy means, for example. So, and bringing these two groups together in one course, I think is an extremely valuable experience for them, because this is a classical situation they will also have later in their professional situation. Doesn't matter where this professional situation will be. So this was the innovative thing. We started with a 3D Navier-Stokes code, and we added, the students had to add two things: the turbulence model, that was the engineering part, and it had to be augmented in a parallel way. So MPI had to be added. That was the programming part. So we organized it with a couple of lectures. There were some soft skill sessions. There were supervised team meetings. Everything was done in a team, and the team always consisted of some computer science students and some mechanical engineering students. Yeah, the reward, of course, was that they got the prize for this nice thing. We have it now for the third time. Every time 14 to 20 participants from different programs. Starts with an introduction, then extension, turbulence, and MPI, and then 4 weeks of a project where each group has to do something with the knowledge, so to write some solver or solve some specific problem. So our experience is, both from the teaching side and from the student side, that this heterogeneity, different cultures in minds, is extremely challenging on the one side, but on the other hand, it's extremely enlightening also, because you make the experience, hey, there is something I cannot do, I need someone else for. But you also make the experience, hey, there is some very valuable knowledge and ability I have and the other guys don't have. And I think this is a very excellent starting point for going into interdisciplinary work. The second example is something we do for increasing the software literacy. So we call this a software project. So we bring together teams of 3 to 8 students, and they shall act for 9 months as a small software company. Their task is to write a specific piece of simulation software from scratch. There is a customer, typically a company, so we did it a couple of times with GE, we did it a couple of times with Siemens, we did it once with Carl Zeiss. And then we try to have a very realistic setting. So everyone of the student team gets a role. We have a project manager, we have a programming expert, we have a model expert. There's a contracting with the customer, specification, and so on. And at the end, there are even fines for breach of contract. Of course, these fines are not in terms of money, but these fines are in terms of grades. So if the thing is done 2 weeks late, they cannot get any more the best grade. So that's the deal. So that's also a kind of as I think, very helpful experience. On the lower left side, you see a couple of topics. We have run this now, very diverse things, if you see. And this has also got some international visibility. We've been invited to present it in a couple of journals over the last years. Now we leave the classroom. So Ferienakademie, the English word would be holiday academy, is some kind of a summer school we have introduced in '84 together with 2 other universities, Stuttgart and Erlangen, for our best students. So it works like a classical summer school. The difference is we do not invite experts, but the students make the program. The students give presentations, the students produce something, whatever. And the professors are just present as advisors for discussions, for guidance, but we don't invite a Nobel Prize winner to teach 20 students for 2 weeks what happens in a classical summer school. So it happens in the Alps in 2 weeks, always during Oktoberfest. There's the idea to prevent students from drinking too much beer and also to prevent us from doing that. It's completely funded by industry and by the 3 universities. We have 12 courses every year, very different topics, also ethics. And it's the idea that we have part of leisure, that's hiking, and the part of intense work. Last year we had a course, Let's Play Simulated Physics for Interactive Games. So the idea was that students should produce an interactive computer game, which was simulation-based, with flow simulation, but also in the interactive part with Kinect and so on. We had 22 students in the team. Again, a very different background: mathematics, computer science, computational science, physics, engineering. We formed 5 teams for the different topics, and even the project management was done by the students. So this was a kind of a challenge because a small hotel in the Alps is not provided with all this technology stuff we need, so we brought along a lot of things with us. The internet connection was not too good, which was not too bad because they had to prepare a lot of things in advance. The game idea had to be developed in the first 2 days, and the main guidance we had to do as professors was to prevent them from being too ambitious. I always said, make it easy, but we would like to do this, but make it easy. You only have 12 days. Think next week, Thursday, everything is over and out, and don't be too ambitious, otherwise you will be frustrated. They decided to make a kind of a boat race game. So here you have a couple of visual ideas. So there's a flow, there are objects, you have a coupled problem already because the flow interacts with the rigid bodies. For the flow, they decided for Lattice-Boltzmann. For the rigid body simulations, they decided for an existing engine, the Bullet game physics engine. For the interaction, of course, Kinect. There are not too many alternatives. Software development should all be done in a very agile way. And also the teaching was done by students themselves. Everyone had to do a short 30-minute presentation to introduce the others to a specific topic. So this was really kind of an inverted classroom. It was inverted, it was no classroom, yeah. So I hope that this works now. This should show the game at the end. So you see the two boats, one of gummy, the other of wood, and you see the red obstacles, and the game is to be the first one who reaches the right side. So you have to move the boat with arm movements for the Kinect system, and now the first player has won the game. This has been done completely from scratch in 10 days. And I think this can only happen if they work all the night. So if something is boring, and we did also a lot of hiking. If it is boring, they don't invest that much of time. So I think that's the most important thing, that you do something which is not boring. I like the middle picture where you see students having climbed on peak on the mountains, taking out their laptops and continuing programming for the game. So a similar thing we have done, we have implemented on PhD candidate level. So we have in Germany this priority program, SPP-EXA, Software for Exascale Computing, which is the biggest coordinated program in Germany. 17 project consortia have been funded. Every of those is interinstitutional, interdisciplinary. Some are even international, one with partners in France and Japan. Education plays a role, so we have introduced a 2-week doctoral retreat for all the doctoral candidates, and with a similar idea, not only work on your PhD project, also get some exchange, look at what the others are doing, and also try to do something together. So 2 years ago, the title was The Fast and the Curious, Exploiting Efficient Algorithms for Fast Hardware. We had some tutorials, and there was also a hands-on part, and at that time we let them program multi-grid algorithms, which are already quite sophisticated solvers on Xeon Phi architecture. Again, there was the most important experience for everyone was this heterogeneity. Even if you take PhD students from a similar funding program, you get mathematicians and computer scientists and engineers, and they have a completely different view on their field. Okay, similar pics, but this time you see the difference, PhD level. My last point is something which is extremely underestimated in the supercomputing world, and this is this excellent piece, student cluster competition at the supercomputing conference, which happens every year. Last year, here in Austin, there were 9 teams of 6 students each before their first degree. So, of course, they're the dominance of the United States, it's clear. We were the only team from Germany. So there are 4 application codes you have to run, a LINPACK, and called mystery application. This is called mystery application because it's not announced in advance. It's just now announced a couple of days before the thing then happens. The interesting thing is that each team is completely free in what kind of machine they build. So they could build up the complete center in Oak Ridge. The only exception is they only get 3,102 watts. If they exceed this, disqualification. There are 2 award categories, the fastest LINPACK and the fastest overall performance. You have to do all the runs within 48 hours. You have to do interviews with the jury members. There's nice accompanying program with social events and so on. So this was our team. It was the first time that we sent the team there. This year it will be the second time. Here you see the different setups of the machinery, and maybe only one thing is interesting, or I want to point your attention to. There were only 2 teams working with accelerators, 1 team with GPUs, and 1 team, our team, with Xeon Phis at that time. So what were the preparations? What had to be done? We had to find a hardware sponsor. We were very international. We found the hardware sponsor in Russia. Travel funds came from Germany, and of course there was a lot of helpful support from Intel through our IPCC. Then the next challenge was find students. How you find the best brains for such kind of a topic. And of course, supercomputing has a visibility, driving to getting the allowance to go to a conference, for our first year students, a student is an interesting thing. So we got the best brain. Among these 6 was even one who won this federal competition in computer science at the high school. Then the students had to get acquainted with everything, that's clear. In Austin arrived, they had 36 hours for building up the machine. All the trials had been done on similar machines in Munich, but not on that one. So when they arrived in Austin, that was the first time that this part was built up after the Russians had been got allowance to enter the United States. Okay, preparations in Munich, on the flight preparations. So this is, by the way, this is a real photo, so we didn't tell them, sit down, please, in a row. That was a by chance shot. Then building everything up in Austin. So why did I say this is underestimated? If you look at the scenery, last year supercomputing conference in Austin, this was in the most remote place, so you really needed a train or a plane to get in this exhibition center. So it's just not understandable for me, why not, if you speak of workforce, if you speak of education, why not putting something like this in the heart, in the center of the conference? Because this is the next generation. This is where the really interesting things happen. My apologies to all industry people, but not at this booth of the vendors. Yeah, but it was in the most remote corner. So we ended up gold medal in the LINPACK and bronze medal in the overall performance. I think this was a good starting point for the first participation. So my last slide, conclusions out of all this. So the most important thing in education is motivation. It's much more important than quality. So this starts also when you select your students. You shouldn't look only at grades. The most important thing is how strong is the will, the wish of the students to really learn something. Make more hands-on project-style things. Let them do more on themselves than the classical, an old guy tells something and everyone else sleeps. Go for special events, some projects, some competitions, some hackathons. This will raise attention and make it attractive. Go for realism. Go for collaborations with the big computing centers. Go for challenges from the applications, either from academia or from industry. And of course, also go for close collaboration with hardware vendors. So our IPCC connection was definitely very helpful there. Fight against this computer science spirit that efficient algorithms is sorting, searching, and this NP strange stuff. Efficient algorithm is high-performance computing. So we are high-performance computing is efficient algorithms. This will increase the attractiveness for young brains. It's the same situation in mathematics. At least in Germany, when students come to the university, they have the idea that mathematics is pure mathematics. The best brains, the competition winners, are all people in algebra, topology, number theory. You have to convince good students, forget about this, go into numerical analysis, go into statistics, go into stochastics. And you have to do this battle, otherwise it will continue that the best brains go in other fields. Okay, they shall do this if they really want it, but they should also get the opportunity to see an alternative. And the last point, of course, this all what I have shown means a far increased investment in planning and mentoring for the teacher side. But I'm really convinced that it pays off. Thanks.